Okay, so welcome to our next laboratory together. And in this lab experiment, we're going to be testing alkenes. Is something an alkene or not? And is there a very quick way that we can determine if a double bond is present? That's what this lab experiment's all about. So, in the lab title, it's called Qualitative Analysis of Alkenes. All right, so let's kind of go through and talk about these scenarios where we can add something to an alkene, get a color change, and be able to report whether or not we feel pretty good about that molecule having a double bond. So before we do that, I want to pull up the lab directions. And that way, if you've got this pulled up on your end, you can kind of follow through and kind of go through and mark your data tables and write your observations and do everything that you need to do as you watch the video. That will be the easiest way for this qualitative lab. So I first want to talk about the term qualitative. What does qualitative actually mean? Okay, well, if this is a new term for you, qualitative means observation-based. That is what we're going to be doing in this experiment. So I don't really have to worry about amounts and making solutions the proper way. It's all about what we see. Now, the other word for this is quantitative, and quantitative has the N, and N means numbers. So that is where I'm going in to calculate concentrations and percent yields and percent recoveries and that type of thing. So that is not what this lab is all about. This lab is about what we see, what we observe, what we write down, and that typical type of data is called qualitative analysis. So in this particular experiment, we're going to be focused on alkenes, and as you know at this point, an alkene is a carbon that's double bonded to another carbon. We can have more than one alkene, meaning more than one double bond. That's perfectly fine. But if it has a carbon double bond carbon, at least one, then these molecules are going to be reacting with these reagents in a particular way. All right, so as I scroll through, they're going to give you some different terminology here. They're going to talk about an alkane. Well, we know that. That's a single bond. They're going to talk about an alkene. Well, we know that now too. That's a double bond. And maybe we've talked about an alkyne at this point in the lecture. And if so, good for you. That's a C triple bond C. But yet we get this thing called an aromatic compound, and this is something that we might not have discussed too much depending on where this lab falls in the semester. So if I wanted to distill this concept of an aromatic compound, what can I say? Well, let's just look for this. It is a ring structure, and a ring structure has an alternating double, single, double, single, double bond all the way around it. This is called delocalization, and when we get a ring that shows us delocalization all the way around the ring, so double, single, double all the way around, then this is an aromatic compound. Not quite 100%, but it at least gives us enough information to make it through this lab, and that's what really this is all about. So this is the term aromatic that might be new to us if you have not made it that far in the lecture material. Now, they also give us a column called saturation. So what does saturation mean? That means carbon has 4 bonds, and those 4 bonds are connected to all atoms. There's no double bond. There's no triple bond involved in the molecule. So if you look at this, this is what we call a saturated molecule, but all of these others are unsaturated molecules. And that's because the carbon here has a double bond, the carbon there has a triple bond, the carbons involved in the ring have double bonds. All of those, carbon is not attached to 4 atoms. One of those bonds is a double bond to one of those atoms, and that's why we call that unsaturated. So again, just some terminology to kind of set all of this kind of stuff up for the qualitative analysis lab. Something else that we probably have talked about at this point as well is not just nomenclature of alkanes, but reactions of alkanes. So here is an example, and this is giving me ethene. Okay, eth, 2 carbons, 1 and 2. And ene means a double bond. So there's a double bond in the middle. So there is ethene, and we are reacting this with bromine. All right, this is a reaction that we've talked about in lecture, folks. You know, when we went through this whole concept of what an alkene is, then we followed that up with reactions of alkenes. And this was one of those reactions. If you remember, we added something like DCM as a solvent, and DCM stood for dichloromethane, or methylene chloride was the common name. So what we said in this type of reaction is that a double bond breaks, 2 sites of attachment open up here and here, and 1 bromine goes onto 1 carbon, and 1 bromine goes onto the other carbon. So we see this bromine getting split in half, and each one of the bromide ions go on to the neighbor carbons. Now, the problem here is that it works with alkenes, but if we have an aromatic, the point here with an aromatic is that no reaction is going to happen. Well, why not? It's got some double bonds. It does, and I'll draw this structure out a little bit more detailed. It does have a double bond. And if you go through here and say, I'm going to break the double bond and 2 sites of attachment is going to open up here and here, and I'm going to put bromine on this one and bromine on that one. That's not what goes on with an aromatic. And the reason is because if you break that double bond, you have destroyed the aromaticity of the compound. What that means is that no longer do we have a double, single, double, single, double anymore. You have disrupted that whole organization. It's like going into your closet one day, organizing everything in the closet and making it look pristine. And then you have this bromine kid that comes in and just decides to grab all your clothes and yank them off the hangers and then laugh at you in your face and then throw a Coke or a candy bar in your face and then run off before it gets spanked or punished or put in the corner or set outside in the cold. I mean, that's up to you, not me. I'm just giving you some ideas. So because it doesn't want to disrupt the organization, it's going to prevent that kid from coming into the closet and destroying everything. So it locks it out. And bromine is that kid. So we see no reaction here with the bromine if we put it into the presence of an alkene. All right. Now, however, if you look at this next example, we do have an aromatic. We see that benzene that's right there. But the problem here is that the double bond that is targeted is not part of the aromatic. So it's okay with this one. And that's because it's not disrupting the ring. It's disrupting another double bond somewhere else that's not a part of the ring. So this does give us a reaction that we can go forward with. Now, here's the thing. Bromine is a orangey brown liquid. So when I get BRs that are grouped together as a combo, we call that diatomic bromine. When diatomic bromine is received in the laboratory and we begin to use it in the lab, that solution is an orangey brown solution. That's just the color that it brings to the table. But when this bromine, the diatomic bromine, rips apart and we get these 2 ions, no longer are those ions colored. Just the bromine that's diatomic as a liquid is colored. So when we rip these 2 bromines apart from each other, and when those 2 bromines basically attack the double bond, get rid of it, bromine goes to the left, bromine goes to the right. When that happens, the diatomic bromine structure is destroyed. And if that Br2 structure is destroyed, then we are also destroying the orange-brown color that it brings to the table. So this is a very good sign that something is an alkene, right? That's what this is all boiling down to. So if I have a bromine source, and that bromine source is added to something that I think is an alkene, if it goes colorless, then that is probably proof that we have an alkene in that container or in that test tube. All right. Now, permanganate is also very similar. So when it concerns permanganate, what we're looking for here is, of course, not bromine. It's permanganate. Manganate? Well, permanganate is MnO4. I see Mn, which is manganese, and that's where permanganate comes from. So in this type of reaction, we've not really talked about this too much. Permanganate will also destroy a double bond. Two sides of attachment open up, here and here. And what we see with permanganate is that it reacts with water, and two OH groups go on to that double bond that's involved in those carbons. We almost form what we call a diol. A diol, di means two, OL means alcohol, and they are side by side. So, permanganate is another colored reaction. It's very similar to bromine. So in the beginning, permanganate brings on this purple color. And this purple color is added to a possible alkene, something that has a double bond with it. And if the double bond is present, what happens is that the permanganate reacts with that double bond, the permanganate destroys the double bond, and the permanganate actually ends up making MnO2 as a side product. And that MnO2 is a solid, and that MnO2 is a brownish red color. So these are the colors. These are the observations. This is the qualitative analysis that we're going to be looking at throughout this lab experiment together. So in the first round, we're going to be dealing with bromine. It's an orangey red color, and it will go colorless if a double bond is present. And then the second round will be permanganate. That permanganate will go brown, not purple, if there's a double bond present. Now, here's the issue. Most of the time, this is done in a general chemistry class or a first-year organic chemistry class, and they really don't want you to be using Br2 liquid. We have it in our lab. We could use it if we wanted to use it. There's no big deal in it. I can go get some DCM, go put some bromine in it, and add these drops to my alkanes and call it a day. However, I'm going to follow the lab directions. I'm going to do what it tells me to do. And because of safety, they're going to use a different bromine source. Because this is fumy, right? It gives off fumes. Bromine actually has a boiling point that's really close to room temperature. So when I take the cap off, I'm going to get all of these fumes of bromine that comes up. And if I'm not careful, I'm going to sniff in that bromine fume. And that's going to react with the moisture in my nose and in my throat. And all of a sudden, it's going to start to make HBr, hydrobromic acid. And now I've just basically swallowed some acid down my throat because I have breathed in that bromine vapor. They don't want this to happen. So because of that, they know that you're going to be working with it. They use a different bromine source instead. And this is called PBP. PBP. That stands for pyridinium bromide perbromide. All right, so pyridinium is this ring with the nitrogen, and bromide, of course, is one of those bromines. And then the perbromide will kind of be the Br2 source because there's two bromines that are left over. All right, that's how I need you to think about this. Not necessarily completely true, but it at least gets us through this particular lab experiment together. So it's just a different bromine source. That's it, folks. That's all that we have to do. All right, so let's look at our procedure. In the procedure, it says, number one, we're going to be looking at a 2% ethanolic solution of pyridinium bromide perbromide. I'll talk about this in just a minute. But if I read the directions, it says labeled 9 test tubes, one for each of the following: cyclohexane, cyclohexene, turpentine, 1-octene, toluene, mineral oil, canola oil, unknown 1, and unknown 2. All right, so it looks like I'm going to have a large assortment of compounds, and I need a handful of test tubes to put them all in. Step number 2 says obtain a sample of each of the 9 and put them into the test tubes. Step 3 says I'm going to add 2 drops of PBP. And then I'll gently shake it. And I'm going to record what color that solution is. And it says if there's no color change, go on to step number 5. But if there is a color change, record that on your data sheet. And then we're going to add 10 more drops of PBP. And if it still remains colorless at the very end, well, we're going to say that this is a positive test. So if we see a color change, that is the overall goal. If the color changes, folks, and it slightly goes away, it might not fully go away, but if it does slightly go away, then this is a very good sign that the compound that I'm using is in fact an alkene. So step number 5 says, if the solution does not become colorless after 2 drops, then you're going to record that as negative, because that means the bromine is staying together. That bromine is not getting ripped apart. That bromine is keeping its color. If it's not getting ripped apart, there's no double bonds for it to react with. That is why this qualitative analysis step is working the way that it is. All right, so I'll need quite an assortment of different things in our lab. And here they are. Here they're all lined up, one after another after another. Well, I'm going to focus on my PBP first. Here is pyridinium bromide perbromide. If you need it, the manufacturer is Acros Organic, and then the lot number is A0290402. And here's the structure yet again of pyridinium bromide perbromide, PBP. All right, so I know I'm going to have to make a solution of this. Remember, it was a 2% ethanolic solution. So ethanolic basically means I need to use ethanol as the solvent. I do not need to use water as a solvent. That would be called aqueous, right? So a 2% ethanolic PBP means weigh out the proper amount of PBP, put it into a container, but use ethanol instead of water to dissolve it with. All right, so I'm going to go to the tiered balance. There we go. I'm going to tear it out. It's not perfectly 0. I'm okay with this, folks. It's not quantitative. It's qualitative. So as long as I ballpark it in the vicinity of what I need, then this test is going to work. That's the beauty of qualitative analysis. All right, so 2% of an ethanolic solution. I looked at this and I said, well, okay, 50 mils. 50 mils, I'm making a little bit more than what I need, but I'm not being too wasteful at the same time. So 50 mils of this. So this is how we do this calculation. 2%, you have purchased a $150, $160 calculator. It does not have a percent key. You're going to have to change that 2% to a decimal, which is 0.02. All right. And you're going to take 2% and you multiply it by 50 in order to get the amount of gram that you're supposed to weigh out. That's how we make a percentage solution. It's 2% of the volume that you're trying to make. So 2% of 50, that value is the amount of gram that we need to use in our experiment. These are the crystals of pyridinium bromide perbromide, and they are rusty brown orangey color, which should not be surprising because we already said bromine is going to be kind of orangey brown in solution anyway. All right, so here's the balance, and this is the mass of the PBP that I have used in the experiment. So 1.0637 is what I have weighed out. If I want a close-up of the PBP, this is what it looks like. So again, if you're asked to do observations, I don't know, right? You might not be, but if you're asked to do observations, there you are. There's a close-up picture of those crystals. As we said before, we need ethanol in order to make that solution with. All right, so I'm going to pull this ethanol away, and this is the ethanol that we're using. The ethanol is lab-grade ethanol from Fisher Scientific, and the lot number here is 7GCC17C02001. So this is what I need to use to dissolve those crystals with. All right, now, that is the first solution that I need for the first part of the lab experiment. But there is another solution that I'm going to have to make. And if I go to part 2, it's going to talk about this 2% again, but this time it's aqueous, KMnO4. So I'm going to do the same thing here. I know I need KMnO4, so I'll pull that from the shelf. Here's the bottle of KMnO4, potassium permanganate. The structure is over here to the right-hand side, K+, and then MnO4 with a negative charge. So this is basically a salt because it carries a cation and an anion, and it can dissolve in water very well. If you need the manufacturer and the lot number, well, the manufacturer here is Fisher Scientific. You see that right there. And the lot number is over here to the side. It's 735499. Very old bottle. It's probably been here since the 80s. Still works. Still good. All right, so I need to go to my balance, and I need to tear that balance out yet again. And then I'm going to use some of the KMnO4, potassium permanganate, to make a solution with. I need a 2% solution. The crystals here, they look black, but they're not. They're actually deep, deep, dark purple, almost a violet color. Don't let the lighting fool you. All right, so here's the balance, and I've put some KMnO4 on it. And the mass that I have weighed out is 1.0963. Again, we need 2%. Hopefully I did the calculation the right way. If not, you can check me. That's a part of the lab procedure. What if I'm just the lab partner and I don't know what I'm doing, and you're just assuming that I know how to do everything the right way? Well, just because I do this for you, don't kind of think that I'm going to do it perfectly for you sometimes. So just double check me. So 2%, well, that means 2%, 0.02, and I made 50 mils in total. So there you go. That gives you a target gram amount, and maybe that is above or below or just the right amount. Who knows? But that's how we do that calculation. All right, so a close-up of potassium permanganate is here. Again, it's going to look very dark to you, but there is violet and purple in those crystals. So depending on your screen and the color, I mean, we've all seen those images. What color is this shirt? What color is this shoe? And then it's like a civil war happens because some people say it's green and some people say it's blue. Well, here's one of those colors. Depending on your screen, this might show up black, or it might show up a deep violet, dark purple. All right, now I'm going to go to the list of everything that I need to pull. Canola oil was one of them. So here's our sample of canola oil. We call this stock because there's no label on it. We ripped it off on purpose because we use it for a different purpose in another lab that we do in our program. All right, so here's the bottle of acetone. I'm not going to give you the structure of acetone. This is something that you can look up if you want to. It doesn't really ask you to do this, I don't think. But if so, just Google it. You'll be able to find it. The acetone is Fisher Scientific, and the lot number is 7GB 420096. The next one's mineral oil, which is Fisher Scientific. And this lot number is 072798. You won't be able to find the structure of this one. You also will not be able to find the structure of canola oil. It is a mixture, a hodgepodge soup of different chemicals that are on the inside. There is no prim and proper chemical structure for either one of them. Octene, you should be able to draw without Googling it, right? Octene, draw it. So 1 octene is acrose organic. And this lot number is A0198034 if you need it. The next one is cyclohexane. You should be able to draw that one too without Googling. That's the beauty of learning nomenclature in organic. Save yourself some time. Use your noggin. So cyclohexane also comes from acrose organic. And the lot number's here, big and bold, B0539339A. Well, it's not over yet, folks. I also need cyclohexene. Again, you should be able to draw that one without a problem. Cyclohexene is also from Fisher Scientific. And the lot number here is 874851. Well, we keep going. The next one they want me to use is toluene. Now, this one you probably don't know, but if you look at the ending, you maybe could get an idea of what this structure is going to be. So this one you might need to look up as well, but here is toluene, and that's also Fisher Scientific. You can see our two companies that we gravitate toward. And the lot number here is 950627. And finally, two unknowns. Here they are, unknown number 1 and unknown number 2. I'm not going to give you the identity of them. You don't need to know the identity of them. That's the part of the lab. So we just need to know, are these alkenes, yes or no? So I went to our cabinets. I just randomly pulled 2. This one is going to be regarded as unknown number 1, and this one is going to be regarded as unknown number 2. All right? So no names. You can't cheat. You can't look up the structure. You have no clue if they're alkenes or not, but that's the purpose of our qualitative test together. All right, so I've got all of my solutions together, and all of my solutions have to be tested. And they don't need to be tested once. They're actually going to have to be tested twice. Oh, gosh. So that means I need 2 sets of test tubes, but we'll get there when we get there. All right, so now I'm going to go back to my solution of PBP. I haven't made it yet. So you can see in the picture, there is my PBP. I'm getting ready to add it to the volumetric flask. So why don't we do it together, live? Not live, but pre-recorded. So I've got the PBP that's here in the weighboat, and I'm just going to transfer this powder as very brown, rusty, kind of reddish color. And just like before in some of the other videos that you've watched, I'm going to crease this weighboat a little bit. I've got a volumetric flask that's here, and I'm just going to pour this solution, or carefully transfer it, into the volumetric flask. All right, so I'm going to zoom out so that way you can see that process a little bit better. And there we go. Creates a nice angle. I'll just tap until I can get all of those crystals down into this volumetric flask. So I'll keep doing this. I won't waste any more of your time, and we'll pick up after I transfer it over. So my crystals have transferred, and now I need to add ethanol, not water. It tells me an ethanolic solution, which means I need to be using ethanol as the solvent and not water from the faucet. All right, so I'm going to slowly pour in this ethanol. As I do, I'm going to pause just for a couple of seconds, give this a nice swirl, and that way you can see what color the solution is going to end up being. So I'm just going to slowly fill this volumetric flask up to the line. The line for 50 milliliters is right here. I don't know if you can see that on the screen or not, but right there it is. And I'm going to make sure that I dissolve it fully before I go up to the line. All right, folks, so you can see the final solution of PBP in the picture. If you need to make observations of the initial solution, there you go. There is a close-up picture of that, so you can make those observations. However, notice that this is a traditional orangey brown color. I would get the same type of color if I use bromine and methylene chloride. Again, though, just for a health and safety reason, they told us not to use bromine liquid and methylene chloride. They want us to use this much safer alternative to a bromine source, and that's why we're doing it the way we're doing it. All right, so the next step is going to be my permanganate solution prep. Notice I have this wayboat here. I didn't take the inside picture, but my permanganate crystals are on the inside there. So I need to make a solution of permanganate, and I'm going to do it the same way. So let's see what I do. So I'm off to my permanganate solution. I've got my permanganate crystals right here. They look black, but they're very violet, deep, deep purple. So just as before, I'm going to fold the weigh dish so that way I can transfer these crystals into that volumetric flask a little bit easier. So I can't transfer all of them, which is perfectly fine. This is not quantitative work. It's qualitative. So as long as I get most of it, that's okay. And that's the beauty of qualitative test. All right, so now I'm going to add water because it says an aqueous 2% solution. So aqueous means water, of course, right? So I'm going to add a little bit of water to that solution. I'm going to give it a good mix. Maybe that purple is showing up a little bit better for you now, so that way you know I'm not lying to you. It wasn't black, it was really purple. And I'm just going to continue to fill up to the line of the volumetric flask, because that line means 50 milliliters, and that's what I'm making here for my analysis. All right, so the line, you can see it, it's right there. Okay, so I'm going to top this off, and then we'll come back together in a few seconds. All right, so just as before, here's the final solution of the permanganate. This permanganate solution was prepped just like ethanolic perbromate solution was, except this was using water because it said aqueous, and the perbromate was using ethanol because it said ethanolic. All right, so again, final observations of the solution. Very deep, deep, dark purple. It is purple. If you look at the top of the meniscus here, you can see that violet color, but it is not a black solution. It's so dark that it does look black. All right, so now I need a set of test tubes, and I'm going to have to label them. And that's what I've done here with just a Sharpie marker. I've brought out my test tubes. Here's the test tube rack. I've written on each one of them what's going to go on the inside of them. All right, so let's take a look at what I do here in order to prep this analysis. Okay, so I'm doing the first part of the qualitative experiment, and this is focused on the PBP. So the 2% PBP is going to be added to each one of these unknowns. And what I have here is a test tube rack, of course, and in the test tube rack, I've got these labeled. So for instance, this says cyclohexane, and I'm going to add a couple of drops of cyclohexane. It says 2 drops, so into the test tube it goes, 1, 2. It doesn't have to be exact. There we go. And I'm just going to set this to a side. So I'm going to continue to do this for all of them and have them all ready to go. And then the next time we see each other, or the next time we speak to each other, or the next time that you watch me, we can add the PBP to those solutions. All right, so PBP is getting ready to be added to all of my test tubes that I've just prepped. So we're going to take this one by one. I'll call out the names. I'll tell you which one that I've grabbed, and I'll add the PBP in front of you live, so that way you can make your observations, because that's what this is all about, folks. All right, so here is a sample of octene. All right, so octene's going to have 2 drops of PBP added. 1, 2. And now I'll shake, and what do you see? Then it says if the color does disappear, we're going to add 10 more drops. There it is.
I'll give it another shake. And again, you write down what you see. All right, so
folks, the reason I'm pausing this at this moment is because I do not want you to get confused. Depending on the concentration and depending on the amount, you could have some residual color that stays behind. So what you're looking for here is the initial 2 drops. Did it go colorless? If so, it's a very good sign that this is positive for an alkene. And this is octene. So you should know that octene is an alkene, therefore it should have a positive test with this. And that's what you saw in the first 2 drops. The first 2 drops went colorless. No more orangey, brownish color that was there. Now, the addition of the extra 10 drops, you might see a little bit of faint yellow that is still there, but that's just because of concentrations and amounts. So if we added a little bit more octene to that test tube, there's a chance that that extra yellow color would have also disappeared. But it is not orangey or deep, deep yellow color like a negative test would give us. All right, so just keep that in mind as you watch these remaining test tubes getting tested.
there's the solution of octene. All right, so I'll go to my next one and I'll keep doing it. So this one is cyclohexene with an ENE ending. There's the solution. You can probably see it in the test tube. 1, 2. I get a shake. What do you see? And now 10 more. All right, on to the next one. Turpentine, 2 drops. Shake. Any color, anything you see. And I'm just going to add 10 more to everything. It doesn't tell me to do that, but I'm going to. And there's 10 extra drops. Next up, mineral oil, 2 drops. There you go. And then we'll just add 10 more. Just to be consistent. There you go. Okay, so I'm moving on to the others. Up next, we have canola oil. All right, so 2 drops. I'm gonna get added in. 1, 2. I'll give it a shake. What does it look like to you? And then I'll add 10 more, again, just to be consistent with everything else. And there we go. Again, observation based. That's what this lab is. All right, up next is cyclohexane with an ANE ending. 2 drops. 1, 2. And there you go. And then I'll add 10 more.
The extra 10 is just so you can see the color better from the screen.
All right, finally, the last one of our knowns is toluene. 2 drops. And then I'll add 10 more. All right, and then we have our two unknowns finally. The unknowns, we don't really know what they are, so I can't really use the name to go by to help me make my decision. So 2 drops gets added to the first, and that's what we end up having. And now I'm going to add 10 more drops. And there it is. And then unknown number 2, or our last one. 1, 2. There you go. And then I'll add 10 more. And there it is. All right, so there's our starting PBP solution. And this very first tube is toluene. The second tube is cyclohexane with an ANE. The next one's canola oil. The next one, that looks like octene. The next one is cyclohexene with an ENE. Turpentine, mineral oil, unknown 1, and unknown 2. Folks, there is the result of the qualitative test for alkenes. All right, so once again, we are looking for a distinction of yellow color that's left behind, because that means it's not reacting with our bromine. So if we see the yellow color, that probably means we don't have an alkene on our hand. So you use your judgment, write down your observations, and fill out that data table sheet. All right, now it's on to part 2.
See how fun qualitative analysis is? Oh gosh, I mean, if people are going to pay me to do this, I'll do it all day long, but I don't necessarily think that it's fun. Do you? I mean, you probably fell asleep watching the video just like I fell asleep doing the lab. All right, so here is the lineup of the alkenes or possible alkenes with our perbromate test, or really our bromine test. That's really what we're after. So this is a still image, so that way you can make your observations. You can pause this video at this point, kind of take a look at what's going on. Some of these testing positive, some of these are testing negative. So it's up to you to really figure out which one is which. Keep in mind, not everything that has a double bond will actually make this color disappear, and one of those we did talk about was something like an aromatic. So if we had an aromatic on our hands, don't be surprised if this doesn't turn the color colorless. It will keep the yellow color because that aromatic ring is not going to be disrupted, and it's not going to change and break apart that bromine. All right, so in the next part, we're going to be looking at permanganate. And we pretty much do this the same way, except we have a standard that we like to use, and we use acetone. And we put some permanganate into the acetone just to give us a reference color. And that's what you're going to see here in this very first video. I'm going to keep that reference tube on the screen for you as we test these other test tubes.
So this next test is the potassium permanganate test, and what I have here to the right hand side is the acetone, and there's 1 milliliter of acetone here. They're asking me to do this as a control, and it says add like 3 drops of potassium permanganate to the acetone, and this gives me a point of reference. That's why we do this. We know that acetone does not have any carbon-carbon double bonds. It does have a carbon double bond O, but not a carbon-carbon double bond. So this is the color that I'm looking for, and if it goes this color, then it probably means that it's not reacting with the potassium permanganate. Notice that has a very similar color to the more concentrated potassium permanganate over here in my flask. All right, so the directions tell me to do this. This sample here is octane, ENE, that has a double bond. So they tell me to add a milliliter of acetone to this sample, and that's what I'm getting ready to do now. There it is. And then to add 2 drops of potassium permanganate. 1, 2. And now we're going to give it a shake. Are those colors identical? Now you can see why we have an issue with the coloring of this qualitative test. This color is not like this one. This is the color of purple. This is a color of like a blood red color, a burnt red color, rust. So we want to add enough drops to see if we can get it to that purple color. But they tell me to stop after 20 drops. All right, so there's 2 drops, and we'll just count them together. 3, 4, I'll give it another shake. 5, 6, 7. 8, 9, 10, 11. It's just getting darker and browner. 12, 13, 14, 15. 16, 17, 18, 19, 20. All right, so after 20 drops, do you see any purple that is there? So once again, we'll set this to a side. Maybe we'll find out a little bit later on after it settles down. But folks, this is what we're after. So I'm going to take the octane. I'm going to set it aside after those 20 drops. If I do get a purple color, it tells me to slow it down. All right, it just tells me to stop whatever I'm doing. Here's mineral oil. And then record that number of drops that it took to get purple. All right, so 1 ml of acetone goes in. So mineral oil, 2 drops of permanganate, 1, 2. And I give it a shake. Is it purple? And then, just to be consistent like I did the other times, I'm just going to add a total of 20. That's 3. All right, so I think that you could count the drops there on the screen, but I think it was very clear what it did within the first couple of drops. All right, so there's mineral oil. Our next one, canola oil. Let's see if this behaves any different. 1 ml of acetone. I'm just going to add the drops in. We start off with 2. 1, 2. What do you think? And now I'll just keep adding. You can count them on the screen. I'll just go to 20 just to go to 20. So that's 10. There's 18. There's 20. Just looks like it got darker. Still purple. Okay, the next one up, bat, toluene. 1 ml of acetone. Two drops of permanganate. What do you see? Is it positive? Again, we know that acetone is not positive, and this is what toluene's already showing me, and that's at 2 drops. I can go on to 20. But it already turned purple within the first 2 drops. But again, to be consistent, there you go. Next up, cyclohexane with an ANE. I'll add 1 milliliter of acetone, 2 drops of permanganate, and there you go, it's already purple. So I could actually stop here in the directions, and for this one I'm not going to add the 20 drops. I think that's kind of silly at this point, don't you? Next up, cyclohexene with an ENE. 1 ml of acetone, 2 drops of permanganate. I'll give it a shake. And there you go. So again, we're looking for this color and this color to match, and at 2 drops it did not. So I'll keep slowly adding because the procedure actually tells me to do this. So 3, 4, give it a shake. It's just muddy brown. 5, 6, 7. Is it purple? 8, 9, 10, 11, 12, 13, 14. What do you see? 15, 16, 17, 18, 19, and 20. So there's 20 drops. Don't really see any purple yet. So I'll set that one to the side. Next up, turpentine. All right, 1 ml of acetone into this one. 2 drops of permanganate. Give it a shake. There you go. Folks, I don't know if that's showing up or not, but this is more red and this is purple. All right, so I'm going to add a few more drops because it doesn't match at this point. So drop 3, 4, 5, 6, 7, 8, 9, 10. Still kind of reddish. 11, 12, 13, 14, 15. 16, 17, 18, 19, and 20. And there you go. All right. Next up is unknown 1. 1 ml of acetone, 2 drops of permanganate, 1, 2, give it a shake, and look at there, one's reddish, one's purplish. All right, so that's a good sign of what it is. 3, 4, 5, 6, 7, 8, 9, 10. Still reddish. 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. I kind of know what this one's going to do. There you go. And we've got one more. This is unknown number 2. 1 ml of acetone goes in. 2 drops of permanganate. 1, 2. And look at there, folks. I can stop there if I want to because those colors look like they match pretty well. All right, so there's 2. I'm not going to add any more. It's already purple. It's a very close match to what the control was, so I can stop there with it. So just as before, we're going to go through and we're going to look at all of them together. Here's the acetone control. My turpentine's next. My cyclohexene. My cyclohexane, A-N-E. My toluene. My canola oil. My mineral oil. My octene, E-N-E. My unknown number 1, and my unknown number 2. All right, so that color of purple is really what we were focused on. And folks, there's a wide view of all of the ones that we've done so far. So which one of these are double bonds, and which one of these do not have any double bonds? That's the question.
All right, folks, so I just did the lab procedure for you. Here is the still image of the very last one that we did together with the permanganate. If you took notes as the video played, you'll know the orders of them if you cannot read them on the test tube, so just go back and replay it. That way you can hear me call out the names one by one. So once more, we're looking for a purple color to stay, and if that purple color stays, then that is a sign that it is not a double bonded molecule. All right, so that's what we're after there. All right, so if I go back to the lab procedure, it's basically going to tell me to do what I just did for permanganate. Add the 2% permanganate. We did that after each drop. Continue adding drops until you reach 20, or the purple color persists after you mix it. If the purple color fades away after you've added 20 drops, you're going to say that this is a positive. If the purple color stays after you've added just 1 or 2 drops, you'll record that as a negative. All right? Okay, so that's what we did. And then a cleanup, of course, I took care of that for you, so you don't have to worry about that at all. So with this lab, there's going to be some questions at the end of this document. You're going to see some post-lab questions. I do want you to answer these post-lab questions. You'll be able to answer these using what we did in the lab together, and you'll be able to use them using the background information that is presented in the lab document. So if one of these questions gets you stumped, just go back to the background, read a little bit about the reactions, and it will tell you what you need to know about these questions. So do the post-lab questions. You're also going to see the data sheet that happens here at the end as well. So once more, they'll give you the lineup of compounds that we tested and the unknowns, and it gives you an area to write your observations, and then it gives you an area to write a positive or a negative test. So it does that with the permanganate, and it does it with the perbromide. Both of those, the data tables look almost identical. Okay. Finally, here at the very last page of the lab document, you're going to see some pre-lab questions. And once more, I do want you to do the pre-lab questions as well. So answer these pre-lab questions. You'll be able to find these answers either in the lab video that you just watched or in the background information as well. So that would be a very good start of where to round up those answers for those questions. All right, so that's basically the lab experiment for the qualitative analysis of alkenes. That's really all there was to it. We didn't make anything. We didn't synthesize anything. There was no reaction that went forward to make us a product. There was no percent yields. There were no percent recoveries. There were no percent errors. There were nothing. It was just an observation-based lab, and it just played off of a double bond characteristic and what it does. And it's just a very quick confirmation test. That's all that it is. Is an alkene present? Yes or no? That is what this lab is all about. And believe it or not, these types of tests are commonly done in a laboratory environment. Qualitative tests are very common, everything from the environmental world to the pharmaceutical world and everything else in between. So this is not a wasted time. This is not filler stuff that we need to worry ourselves with. There's actually a practical use for these types of qualitative tests. And here you've just seen 2 of them. And there's many, many hundreds more. All right, so that's it of the qualitative analysis. Good luck on the lab. If you have any questions, you know how to get a hold of me, and I'll answer you shortly. So until the next lab together, I'll see you at that point.